Okay, so this section is hopefully going to be pretty short. I want to have a simple point I want to make. Let's see how efficient I can be. Chapter 7, Section 3, Light from Atoms. What does it mean? Oops, misspelling there. Let's fix that. Okay, so I have a pretty simple point I want to make in this section. Tro does too, or I guess I'm just making his point. Here. Okay, I have a pretty simple point that I want to make here. I think Tro's not saying a whole lot in Chapter 7, Section 3. So let's see how efficient I can be. Light from atoms. What does it mean? Okay, so what does light and let's see, what do light and atoms have in common? What's the point with this, right? The title of this section is Atomic Spectroscopy in the Bohr Model, and let's see if we can see this as a simple take-home. So first of all, it's important to appreciate that in the 1800s, when was this? Late 1800s? In the late 1800s, Johannes Rydberg, I don't even have a date on this. Johannes Rydberg took hydrogen, okay, and ran electricity across it, and essentially excited electron. He didn't know what he was doing, okay, so he ran a charge across this hydrogen gas, and then light came off, and he put it into a sheet, right, by putting it through a slit. And then through a prism, and son of a gun, the light spread out like it does in a prism, but it didn't spread out into all frequencies, okay, or all colors. It did not. So the hydrogen came out, and it spread out to like 4 colors. Remarkable. Red, cyan right here, blue, and then violet, okay? And then he did it again with helium, and it got different colors. See this? Blue, another blue, green, I guess. Whoops, whoa. Blue, another blue, green, yellow, red, right? This is the helium. Then he did it with barium. So same thing, right? Made a lamp. Then he put the light that was emitted through a slit here, made it into a sheet, or a ribbon. Can you see a ribbon of light right here? Through a prism, splits it up, and finds, wow, it gives different colors of light, okay? And if you do this to white, it gives all colors. All right, so what's that about? Well, Niels Bohr came along and said, you know what? I have a feeling that maybe these different colors correspond to different wavelengths of light that electrons are emit when they're relaxing from one energy level to another. Okay? I know that was a mouthful. That was a mouthful. All right, so look what we have here. This is the Bohr model of an atom. This is the nucleus of the atom. And here's the first shell, n is equal to 1. Here's the second shell, n is equal to 2. The third shell, okay, you see where I'm going with this? 4 and 5. Now, if an electron drops from the third shell to the second shell, it lets off a photon of red light. It lets off some energy. It lets off the energy in the form of a photon. The wavelength of the photon is 657 nanometers. Okay? If an electron drops from the fourth energy level to the second, it lets off a photon that has a wavelength of 486 nanometers. Okay, you see that? And if it goes from the fifth to the second, it lets off, okay? And so what Bohr did is he said, oh, I wonder if these different colors correspond to different wavelengths, or rather I should say different energies, okay? He didn't quite go to wavelengths right away. Okay, correspond to different energies. And sure enough, it's the difference in the energy. So let me go back a second here, okay? So that red is the energy difference between two orbitals in a hydrogen atom, okay? This one, where's my mouse? That is the energy difference between two other orbitals, okay, or two states. Let me say that. Two states of an electron. This color is a different energy level. I'm sorry, another difference between two energy states, okay? So the hydrogen is relaxing, the electrons are relaxing in the hydrogen atom, and when they are, they're letting off this energy, and it's this energies that we see are four different ones. Helium has got 6 different ones that we see. Barium's got a bunch, okay? And then white has all of them, right? There's lots of different photons, or energies of photons that show up in white light. Okay? So Bohr came along and said, I bet you these are energy differences. Okay? Now, I will tell you, this is good news and bad news. The problem with this is the barium and helium were way too complicated to make any predictions with. He could make predictions that worked for hydrogen, but the other ones, he just couldn't do anything with them. Okay? So the Bohr model of an atom, with the Bohr model of an atom, we're going to treat all atoms as if they're like hydrogen. I know. Let me say it again. In the Bohr model, we're going to treat all atoms as if they're like hydrogen. Okay, that'll make more sense as we do some problems.